Okay, in this video, TL2, we are going to discuss open and short-circuited AC transmission lines. These are transmission lines with sinusoidal signals on it, so everything is assumed to be at a steady state. And we're going to consider a transmission line that ends either with the two conductors of the transmission lines connected together, or it ends with nothing, or if you prefer, an infinite resistor. So this lecture will actually be divided into 4 parts. Part 1, we're going to expand our understanding of what impedance means and discuss reactance as well and connect that together. In part 2, we're going to talk about a transmission line that ends in a short circuit and how it evolves as a function of the length of the transmission line and the signal that we put in. In part 3, we will talk about an open transmission line, which is a transmission line that ends in nothing, and we'll compare that to the shorted transmission line. And in part 4, we're going to talk about reactive loads, which are either inductors or capacitors. We'll talk about the idea of resistors in a load will come up in the next lecture video, but today we'll just finish on reactive. So part 1, impedance and reactance. Let's dive into that. Okay, so let me just start out by writing the definition of a capacitor, right? A capacitor behaves in the following way, that the current across the capacitor is equal to the capacitance C times the time derivative of the voltage. All right, now this of course is in the time domain, but we're now considering everything in terms of a phasor. And so if we have sinusoidal variation, then we are simply capturing the amplitude and the phase of the signal in this phasor value, which can have a real and imaginary part to it to capture all of that. All right, so in the phasor domain, the time derivative of something in the time domain equates to multiplying by j omega. If you go back to the definition of a phasor, that V as a function of V as a function of t equals the real part of the phasor value of V times e to the j omega t. The e to the j omega t just causes our initial phasor value, V squiggly, to spin around. It rotates around f times per second. And so when we take the time derivative of what's on the right side, it ends up being the same. We just have to multiply it by a j omega because this pops out of the exponent when we take the d dt. So this time domain form, if we convert this into the phasor form, will look like this. I phasor equals C times J times omega times phasor value of V. All right, this is the same equation, just converted into the phasor or frequency domain form if you prefer. All right, now from this we can define the impedance of a capacitor. Right, there is a ratio of current to voltage that we can very easily define from this equation, and this equals the phasor value of V divided by the current value in phasor form. And this works out to be minus J over omega times C, where omega is 2 pi times the oscillation frequency and C is a capacitance. All right, the important lesson here is that this is a negative imaginary resistance or impedance, negative imaginary impedance. So we can treat a capacitor as if it were an imaginary resistor, a resistor with a imaginary value. In this case, it's a negative imaginary value. All right, now this has 2 pieces to it. Number 1, there's the 1 over omega C part, and that simply is going to scale things, right? It's going to scale the size of the current compared to the size of the voltage. They're going to scale together, but the impedance tells us what the proportionality constant is. What the negative J is going to do is it's going to imply a 90-degree phase shift between the voltage and the current. But apart from that, it doesn't really mean much else, right? So minus J means 90-degree phase shift, and the minus tells you which one is ahead of the other. There are a little more details in the notes about what a 90-degree phase shift between them means. But we can repeat the same process for an inductor and define an impedance of an inductor. And this is the voltage as a phasor divided by the current as a phasor. And this works out to be positive j omega times the inductance L, or this is a positive imaginary impedance. So once again, an inductor can be thought of as an imaginary resistor, but it's a positive number. What that means is that there is still a 90-degree phase shift between the voltage and current, but 90 degrees is the other way. It's a question of whether the voltage leads by 90 degrees or whether the current leads by 90 degrees. And that's what that positive or negative sign indicates. It also has a different relationship of omega and L, which is on the numerator instead of in the denominator. And that just kind of comes from, if you just examine the equations of V divided by I, you can sort of see that that's just sort of pops out. And it should make sense, because if a capacitance is really large, then that means you put in a lot of current and you get only a very small change in current. All right, so if the current is really big, you get a small voltage. That should imply a very small impedance, and that's the case, right? A big value of capacitance gives us a small impedance. So this all seems to make sense. Once we treat inductors and capacitors as imaginary components, we can combine them with resistors in pretty straightforward ways. For example, if I have a resistor in series with an inductor, this is R and this is L, I can treat that as being just like a single device that has impedance Z, where Z equals R plus j omega L. And I can figure out what the voltage to current ratio is across this entire device simply by, again, calculating R plus j omega L. Right? And you can do the same thing with resistors in parallel. You can treat them just as if these were resistors and apply the same mathematical techniques that you would have in your circuits courses. All right, so that is the idea of impedance of an inductor or a capacitor expanded. And the most important thing to remember is that a negative imaginary value refers to a capacitance, and a positive imaginary value of the impedance refers to some inductance. All right. Now, I want to define another concept called input impedance. It's going to be very important. And for that, let me just draw a simple circuit diagram where we have a transmission line connected to some unknown load, and this load is going to have an impedance Z, and the intrinsic transmission line of the impedance is going to be Z0. All right. I'm going to define a new concept called input impedance. I'm going to draw it like this. And it's a question, what is the apparent input impedance viewed from this point looking into this transmission line? All right, so while Z0 is the intrinsic impedance, and we define that pretty clearly as the square root of L over C, Zin is what we're going to call the input impedance. To understand what input impedance is, I want you to consider the following. Let's say on this transmission line, we're going to inject a voltage here. We're going to have an input voltage as a phasor, and we'll have an input current as a phasor. And this voltage and current is going to propagate down this transmission line. It's going to hit this load. There will be, in general, some reflection, and it's going to propagate back out to the end. And when it exits, we're going to get a certain output voltage and the output current. All right. Now, what's different about AC transmission line is that we have a defined relationship between V in and V out. Because if we know this distance, then we assume it has a distance d, then we know what the phase shift of this sinusoidal wave is going to be from this original point propagating down to the load, right? Beta d is the phase shift from the input to the load. right? And the same at the output, right? There is also an output that after reflection, you're changing the phase on its way out to reach the exit point where you originally injected things. And so Zn, in order to sort of correctly calculate the apparent input impedance, we sort of have to add up what goes in and what comes out in the following way. So the definition of Zn will be the following. It will be V in plus V out as phasors divided by I in plus I out, also as phasors. And in this case, we know how Vn is going to relate to In because the transmission line impedance does define that for us. Right? It's going to be In Vn divided by In must equal our transmission line impedance C0. Right? And V out divided by I out will also equal to our transmission line impedance. All these are both phasors as well. Right, so for each of our incoming and outgoing wave, the ratio of voltage to current must be this intrinsic impedance C0. But the total, the sum of the voltages divided by the sum of the currents is not going to be the same as Z0. It's going to be more complicated than that, and we'll see. We can actually rewrite Zn in more complicated form later. I'll leave that out for now. All right, so don't confuse intrinsic impedance with input impedance. They're very different. Intrinsic impedance has strictly to do with the inductance and the capacitance on a transmission line, and that's geometry, that's the materials in a transmission line, whereas the input impedance also has to do with the geometry, how long your transmission line is, and what your load is. All that is going to factor into the input impedance, and it combines all that together. All right. So those are going to be a couple of important concepts that we're going to use to expand our treatment of transmission lines into the AC circuits. In the next video, we are going to sort of see what happens when you apply this definition to a transmission line that ends in a short circuit.